So in this video, we're going to look at problem 3.44. We're in three-dimensional space, and we see that we have five forces acting upon this particle, F1 through F4, along with a 225-pound applied force. If we're told that the magnitude of F4 is 165 pounds, what we want to determine is, can we solve for the magnitudes of F1, F2, and F3? And before we get started, let's think if this is even feasible. Well, what do we know about equilibrium in three dimensions? Remember that generally speaking, in three dimensions, we have three scalar equilibrium equations, namely the sum of all forces in the x direction must be zero, the sum of all forces in the y direction must be zero, and the sum of all forces in the z direction must be zero. So with those three equations, we generally can solve for three unknowns. So as long as we have all of the geometry information about F1, F2, and F3, and those forces are characterized only by their unknown magnitudes, it is feasible that we could have a statically determinate situation with the three equations that we have. So really, it's just going to be like most problems that involve equilibrium. The first thing that we need to do is to decompose each vector into its Cartesian form. And of course, three of the vectors, F1, F2, and F3, will have a single unknown in that decomposition, but that's okay, right? We're just going to, as long as we only have one unknown, we will be able to solve. So let's begin by looking how the decomposition of F1 would work. Look at F1 here, and you might think, oh, it's in the XY plane. But note that there are actually three angles that are specified. This 60-degree angle, this 60-degree angle, and this 135-degree angle. And what do you notice about each of those angles? They're angles that are measured to the vector from a coordinate axis. So if you remember what we defined that as, and I believe it was chapter 2 originally, those are just your coordinate direction angles. This is your alpha from the x-axis, 60. This is your beta from the y-axis, 60. And this is your actual gamma. So remember that when you have the coordinate direction angles of a vector, you can decompose it into Cartesian form by simply multiplying by what's known as the direction cosines. And the direction cosines are just the cosine of those coordinate direction angles. So particularly for F1, if you want to decompose it into x, y, and z components, you would multiply the unknown magnitude F1 for the x component by the cosine of 60 degrees. That's cos alpha. For the y component, you'd multiply the unknown magnitude F1 times the cosine of 60 degrees. And for the z component, you'd multiply the unknown magnitude times the cos of 135. And I posted a solution starter for this. I didn't give you the whole thing that actually shows how that decomposition is done. The coordinate direction angles were given, alpha, beta, gamma. So we multiply by the cosine of those angles, which is often called the direction cosines. Now, what we notice is that a lot of the other vectors are pretty simple. F2 and F3, along with the 225-pound force, they're just aligned purely along the coordinate axes. So the only mistake you can make here is not being careful with your signs. Note that F2 is in positive z, however, F3 is in negative y, and the 225-pound force is in negative x. So when you actually show the decomposition there, make sure that you put in the negative signs appropriately for F3 being along negative y, and for the 225-pound being along negative x. So the last thing that we have to do is talk about how we would actually decompose F4. So F4 is a bit different in that the two angles that were given to describe its geometry aren't coordinate direction angles. Now you might ask, well, why aren't they? Well, if you notice, these angles aren't measured from the vector to a coordinate. 45 degrees is measured from the vector to the xy plane. So this is traditionally called an elevation angle. And if you notice, it can naturally be used to decompose the vector into a component along the z-axis and a component in the xy plane. And if you recall, we called that component in the xy plane the projection of vector F4 into the xy plane. Once we have it projected down into the xy plane, we can decompose it further into x and y components. But let's begin by talking about how we can decompose F4 into a z component and a projection into the xy plane. So you can just redraw that triangle like I did here and just show that there's a 45-degree elevation from the xy plane. If we do this decomposition, the z component will point in the upward direction. Its magnitude is going to be given by the magnitude of F4 times the sine of 45 degrees, since it's opposite. That's what I have here. And this component, which is along the base of this triangle, which is related to the cosine of 45, remember, it's just the projection of F4 down into the xy plane. Now, be careful, because once you have it in the xy plane, don't lose track of which quadrant it's in, I should say. It's going to project down into the positive x but negative y quadrant. So I think it's good when you actually draw your decomposition further to show the positive x-axis, the negative y-axis. There's your projection, and what angle are you given? You're given the angular separation between that projection and the positive x-axis. If you look at it, that's the 30-degree angle. So just like always, draw your force decomposition. It decomposes into a positive x and a negative y component. The angle of reference that we're given is 30 degrees. So if we know the projection along into the xy plane, The x component is just going to be related to the cos of 30. So how do we actually write that? Well, it's going to be this magnitude, which is the projection of f4 into the xy plane, times cos 30. But don't you forget that you have the projection of f4 into the xy plane above. It's just f4 cos 45. So just like all problems that involve azimuth and elevation, whenever you project a component down into the xy plane, you're traditionally going to have two trigonometric functions there. So don't be surprised if you have something like cos 45, cos 30. The first cos 45 puts it down into the xy plane. The second cos 30 brings it to the x-axis. Be careful, do the same thing for the y component, but notice that it's pointing in the negative y direction. So that's why I've added this negative sign in to actually make sure that I'm consistent with my coordinate axes. So now that I have F1 through F4, along with the 225-pound force decomposed into Cartesian form, I know that if this is an equilibrium in three-dimensional space, the sum of all forces in the x, y, and z directions must be 0. So if you go forward and you look through what you'll get in terms of scalar equations, when you sum those up, notice F1, it has an unknown in the x component, the F1 cos 60, but F2 doesn't, and F3 doesn't. And F4, even though it has an x component, remember that that's one of the quantities you're given. You're given 165 pounds. And of course, the minus 225 is in the x direction as well. However, when you sum all forces in the x direction and set it equal to 0, what you'll find is even though you generally have three unknowns in your system, you're able to solve for F1 uniquely. So this is a very decoupled system. If you actually write it out in matrix vector form, you'll see that your matrix is a bit sparse. So what I mean by solving it iteratively is if you sum all forces in the x direction, that will allow you to solve for F1. Do the same thing for y and do the same thing for z. And what you'll find is, unlike the problems that we worked in 2 dimensions previously, which were fully coupled equations that you had to solve through some sort of simultaneous technique like substitution or elimination or so on, these are going to be much more easy to solve through sequential substitution or iterative substitution.